Hello, Advanced Physics. This is Dr. Berenzi, and this is a video on lesson 8.2. And in this lesson, we're going to be able to calculate the magnitude and direction of the electrostatic force between two or more charged particles in two dimensions. So it sounds like a lot of words there. Let's figure out exactly what we mean by those words. So, going to the next slide here. Looking at this top picture right here, so I have three charges that are lined up. How do I calculate the net force acting on this charge here in red? Well, hopefully what you learned in lesson 8.1 is that you take these two charges and you calculate the force between them. So the force of this charge acting on Q3. You figure out what that force is, and then you look at this pair of charges and figure out what the force of Q1 acting on Q3 is, and then you find either the sum or the difference of those. So you just need to do some addition or subtraction. Now, how would we handle the situation if we decided to actually put these charges at an L shape or in an L shape instead of in a straight line like up here? Would I be able to simply just calculate the force that this charge exerts on this one and then take the force that this charge exerts on this one and then just simply add those two numbers to get the net force? Well, it turns out that the answer is kind of, but not really. I wouldn't add up the numbers, so I wouldn't do addition with numbers, but I would do addition with something that we haven't talked about in a long time, and that is addition with vectors. So, in that second case where we have this L shape, what we need to do is use vector addition instead of just regular addition. So if this is the force caused by charge Q3 and this is the force caused by this other charge over here, then what I need to do is I need to add those using vector addition. So I need to take one of these vectors and then add the other vector to it. And remember, with vector addition, couple of rules. First of all, tail to tip. So I have to take the tip of, or the tail of one of these vectors. In this case, I've taken the tail of this vector and placed it on the tip of that vector, and that's how I get these two vectors to look like that. And then what I have to do next is then connect them from start to finish. So tail to tip, start to finish. All right. So let's take a look at an example that actually involves vector addition. So what is the magnitude and the direction angle of the net force on the 5 microcoulomb charge? Okay, so let's come up with a strategy first of all on how to figure out what the net force is acting on this -5 microcoulomb charge. What I like to do first is I like to identify where that charge is that I'm interested in, and in this diagram it is this one at the corner of the L, so I'm going to put a star next to that to remind myself that that's the charge that I am concerned with, that I want to find the forces on. And then what I'm going to do is I am going to take one charge at a time and calculate the force from that charge using Coulomb's law. So I'm going to take these two charges first and only look at those two charges and calculate what the force is from this charge down here. And I see that this is a negative charge. This up here is a negative charge. And since they both have the same charge, they are going to want to repel one another. So this charge is going to actually is actually going to be pushed away. So that would be up in that direction. So that first charge is going to exert an upward force on this -5 microcoulomb charge. And then I need to now think about the other charge here. So I'm going to now think about these two charges here. And I ask myself, okay, this is a negative charge. This is a positive charge. And those are opposite charges, so these two charges are going to be attracted to one another, which means that this charge is going to want to be pushed toward the right. So I have two forces acting on this charge up here. One is pushing up, the other is pushing to the right. And now I just need to figure out what the magnitude of those forces are, and I can do that using Coulomb's law. All right, we learned that in lesson 8.1, so if you need a refresher on using Coulomb's law, by all means go back to that video and I have some examples there. But we can do this very quickly here, so let's go back to these two charges and first calculate F1. So I'm going to just write out Coulomb's law for those two particular charges. K times Q1 times Q2 divided by the distance in between them. And don't forget, we need it in coulombs and in meters. And when I evaluate that, I get 0.36 divided by 0.0144. And when I figure that out, that ends up being 25 newtons. So this force pushing up over here is a force of 25 newtons. Okay, now I don't have any more room on my slide here, so I'm going to erase all this stuff right here. But I do not want you to erase it. I simply want you to continue down on your sheet of paper there, because now I have to calculate this force right here. So now we're going to turn our attention to those two charges. And now let's calculate what F2 has to be. So we're going to again use Coulomb's law. So F2 equals K times Q1 times Q2 over the distance in between the two charges. Okay, when I do that, I get 16.7 newtons. So this force is 16.7 newtons toward the right. Okay, so once I have calculated the magnitude of each of those forces, now I can draw a set of vectors and then connect them tail to tip and figure out what the magnitude and direction of that net force vector is. So let me show you what that looks like. Again, I'm going to have to erase this stuff because I'm out of room, but don't erase it on your paper. Just go ahead and draw below what you currently have. So let's erase that. And now what I want to do is I want to draw these two vectors. And I would probably at first draw them like that, but then these are not connected in a way that allows me to do vector addition because they're not tail to tip, right? I have the two tails connected together. So I need to move one of the tails over to the tip of the other. So first we have to do tail to tip. It's usually better to actually move the y facing vector, this one, so that it's at the tip of this vector right here. And the reason that is because, actually I'll tell you when we're calculating the direction angle why we do that, but just accept that for now. So I wanted to do, this is what it would look like when I've connected the tail of this vector to the tip of this vector. So now I have tail to tip. And then the second thing I need to do when I do vector addition is go start to finish. Okay, and that means that I have to start where the two vectors start, and I have to finish where the two vectors finish. So I have to draw a vector from the start point up to the finish point right here, like that. Okay, that is going to be my net force vector. It's a vector that's pointing up and toward the right. Okay, again, I have this problem of running out of room. So what I'm going to do is I'm going to erase this part. Do not erase that part on your sheet of paper. Just go ahead and write below again. And let's actually figure out what the magnitude of this net force vector is. Well, in order to figure out magnitude, magnitude is the size or the number of this net force. And in order to get that, I have to use the Pythagorean theorem because I have created a right triangle here. So let's go ahead and do that. So F net is equal to the square root of the squares of the two legs summed up together. Okay, C equals the square root of a squared plus b squared. And now I am going to evaluate this, and when I do, I get a net force of 30 newtons. Okay, so I've answered part of the question. I've answered what is the magnitude of this force. It turns out to be 30 newtons. But now I have to ask, what is the direction angle? And the direction angle is usually measured with respect to the x-axis. That's the way that we typically do it in math. So we usually identify theta, this direction angle, as with respect to the x-axis. So I'm going to take this x-facing vector and identify this as theta, our direction angle. And this is actually the reason that I chose to move this vector, because I wanted this angle to be inside my triangle. If I'd drawn it the other way, I would have a triangle that looks like this, and I wouldn't be able to define a direction angle with respect to the x-axis. I would end up defining one with respect to the y-axis instead. And that's not what not what you typically did in math class. So move the y vector. That's all I have to say about that. So move the y vector. Now, how do we figure out what this angle is? Well, we can use our trig functions, and the vectors that were given to us were the opposite side and the adjacent side. And if I remember right, opposite over adjacent gives me tangent. So the tangent of that angle has to equal the opposite over the adjacent vector. If I want to solve for theta, I take the inverse tangent on both sides. So I get theta equals inverse tangent of 25 over 16.7. And then when I figure what that number is in degrees, I get 56 degrees. So this is a 56 degree angle. Okay, so that's how you can use vectors in order to figure out what the net force is acting on this -5 microcoulomb charge. It's going to be a vector whose magnitude is 30 newtons and whose direction is up and toward the right at an angle of 56 degrees with respect to the x-axis, or the x direction. Okay, so good luck with the homework, where you're going to be challenged with similar problems with charges in 2 dimensions, and I look forward to seeing you soon. Bye.